Hey folks, Todd Coburn here with your Aerospace Structures series. This lecture is on sandwich structures, and this video will focus on design and analysis of these kinds of structures. Let's see how it works. So whenever I think of a sandwich, I think of one of these puppies, but we're actually not talking about that kind of sandwich. We're talking about a different kind of sandwich, which is maybe less tasty, but just as useful. We're going to loosely use this term sandwich to talk about any kind of structure where we have three or more materials. Usually we have a very dense, strong, stiff material, and those are going to be our face sheets. And in between, we're not looking to put something in there that's weaker, but we're looking to put something in there that's lighter. And lighter materials will typically be less dense and have less stiffness and strength. Now, so we're going to be looking at these ideas and how they play out. It's kind of, so one way to bring this back into our intuition is to think of I-beam structures. Remember when we were talking about from the beginning of our journey in structural mechanics, looking at stress analyses and material behaviors, we've seen that if we can remove area from the cross-section where it's not needed and place it instead where it is needed, we can get a lighter, more efficient structure. So when we have bending structures that withstand bending, getting the area away from or leaving the area that's away from the neutral axis or even pushing it out further and removing any material from the center of the beam where it carries it's less effective for bending. Now the trick here is we still have to have attachment between the two face sheets. It's called shear continuity because everything between, while it doesn't need to have a lot of axial stiffness, it needs to have enough shear stiffness and strength so that these two face sheets act as one. And the way we did that previously was typically using an I-beam where we push those face sheets away with a really thin web. This web has a lot less area, so it's weaker and it has less shear stiffness because a lot of times that will be stability critical. It can buckle out at a very low number when you get really thin webs like we see in aircraft and shipbuilding and things like this. But the structure is very efficient for carrying bending. Now, if we're only carrying axial load, we can just have a solid material, a little block like a round or a square section. But if we're carrying bending, then we want to remove any area near the neutral axis and leave the area that's far away from the neutral axis and even get more area out there and push those further apart. So the sandwich beam, which does this with two face sheets and some kind of, usually it's fully filled, less dense material in between, versus the I-beam, which typically has solid structure that is just designed, the shape is designed to provide that. These are going to give us the best resistance to this kind of load. Now, if you look at the Hexcel data sheets, this one, this little figure on the left is from TSB 124, and they show a typical ratio, like if you have a solid rectangular block of material, and if your relative stiffness is 100%, it shows how your stiffness, strength, and weight change if you just take, so you take that first solid material, it has T, and you take half that thickness, and you push it 2T away, make it twice as thick, but split the middle of that and put some kind of low density core, you can make it 7 times more rigid, 3.5 times as strong, and only a 3% increase in strength. Now, obviously, this is assuming certain properties for the core material. If you then go on and you make that 4 times as deep, so we've got basically the same face sheets with just a little bit of added core. If you make that, spread that 2 half thicknesses so that it's 4T times total thickness, you can get 37 times more rigidity, over 9 times more strength with only like a 6-ish% increase in weight. So this kind of gives you a feel for the kind of payback we can get for these kind of structures. And here's a little sketch of a typical sandwich beam. We'll be focused in on that in a moment. You got those basic ideas? So the basic idea here is we're building a bending beam. That's a common usage for sandwich structures when we need good bending resistance, and also we need something that's continuous so somebody can walk on it, or maybe have a pressure load or something like that. We also can use sandwich structures for other things. We'll talk about those briefly in later lectures. Okay? So with those ideas in mind, then, we can kind of look at this idea further. So once again, remember, relating back to an I-beam that we're familiar with versus a sandwich structure where we have some kind of continuous core material underneath the face sheets. Now, not all sandwich structures have continuous material inside. Sometimes you have corrugated honeycomb, which also, while it tends to be more uniform than just empty space like an I-beam, it is not completely filled like you get with like a foam or something like that, or a balsa core or something. But if we take a look here and just evaluate, imagine what would happen if we applied a point load to this. Now, depending on where you put the point load, you can see that a point load on this I section is going to tend to bend that I section, the flange, quite a bit. While even though the core is a lot less rigid than the solid material of the I-beam, if these were like an equal thickness, at least that's uniformly supported by the core, so it can tend to be, a sandwich can tend to be more resilient to point loads, where an I section, you're going to have to be careful to load it up through the key axes of the cross section. So that's just kind of a rough design idea that we need to be aware of. Now, these pictures, I've got a couple sketches in my book. I pulled some of these, are a little fancier off the internet. This shows a typical sandwich construction. This is face sheets are often aluminum, or they can be steel. They can be really any material, including wood. A lot of times composite, graphite epoxy, or fiberglasses are used. You name it, you can take different face sheets. So we're looking for something that has relatively good strength and stiffness for the face sheets. And because we're going to get our strength and stiffness by pushing them far away, these tend to be very thin. The thinner the better, actually. The reason we go with a thicker face sheet is usually because we need to withstand punch loads. If we just want to withstand more bending, we usually don't thicken up the face sheets unless we have a space constraint. What we'll do is just push those face sheets further apart with more thickness of core to get a more efficient structure, and a more efficient structure, and a more efficient structure. But if we have somebody walking on, or there are point loads that are applied to the surface, then we're going to need to thicken up that face sheet, or both face sheets, in order to withstand those, so that load can distribute to that soft core. Often we're also going to be using adhesive between the core material and the face sheet. Now, some face sheet materials will bleed down into the core and bond. Some core materials will bleed up into the face sheet and bond, but generally we're going to have an adhesive. A lot of times a film adhesive is used for this, but you name it, you can probably find it. And that results, this is kind of an exploded view, and then that results in a typical sandwich kind of structure. There are a number of different other kinds of cores that can be used, both engineered and just raw materials. Here's just a picture of a few pulled off various internet sites. Okay? So if we think, before we get started with our analysis, think about some applications. Look at this little structure here, and this is one typical kind of application, certainly by no means the only one. We're looking at this, and you can see we've got a core here, and you might ask yourself questions like, what is this structure? Well, this looks like the leading edge of a wing or a flap or something like that. And in those cases, you can see you've got your structural members. You can see looks like solid material stringers back there in the background. We can see face sheets carrying the load, but then on the leading edge, where you get a lot of dynamic pressure applied, in order to keep that shape, you're going to get pretty good resistance just from the curvature of that structure. But then by making that a honeycomb or a sandwich kind of structure, it will resist even more localized bending than it otherwise would. So if you get a bird strike or something like that, that's going to be more resilient. You can see that that's providing, in this particular case, more bending, localized bending capability that's continuous across that leading edge. Here's another little application. In this case, it looks like we've got our arrow shape is formed by thin composite, and they're using that sandwich structure as like a column material. Now this actually is just for getting some column-like, probably better, so it doesn't, that stringer doesn't buckle out. Probably not the most efficient use of sandwich structures, but it can certainly be used for that as well. And here's another little piece when we have smaller pieces that need to be able to react localized forces. A lot of times we can make that use a really low density foam or honeycomb core and then cover it with face sheets to get a pretty efficient structure. Let's take a look at nomenclature before we start getting into the analysis. Here's a typical beam. You can see the face sheets and the core material, and it looks kind of like this is a honeycomb the way I drew it, but really it could be any kind of core material, continuous or not. There's a few parameters we're going to need. We're going to obviously need the length of the beam, what's the effective length, and what is the effective width. We'll usually use L for length and B for width. W also works for width, but B is a very common variable name for that. We're going to have some kind of loading. It could be a pressure loading, could be a distributed loading. In this particular case, I'm drawing a point force. And we have this parameter h, lowercase h, which is typically the distance between the midplanes or the center of the face sheets. So from face sheet center to face sheet center. If we look at a cross section of this beam, just looking down the end, that's what I drew at lower right. And you can see we have two face sheets and an unknown core material. You can see the overall dimension of the sandwich I'm calling capital H. This nomenclature is not as universal, but that's nomenclature that I've honed in on. I started tightening up my nomenclature when I started teaching, as I realized that students and industry professionals were getting confused about some of these variables and when they're used. An industry professional who has a lot of experience sometimes will switch variables because they have the knowledge to know which one means what. But when these variables are switched around for somebody that hasn't worked on it as much, it's quite confusing. So I typically use that capital H for extreme upper surface to lower surface. We're using that H that I talked about, the lowercase h, that's the midplane of the upper face sheet to the midplane of the center. This is a very important to mention. And the variables that are feeding into this are the face sheet thicknesses, which I'm defining as T upper and T lower, and the core thickness, T core. So these variables are all related. The one we're going to use the most, we're going to use all these, especially the face sheet thicknesses and the core thickness, but this H parameter is going to be one of the keys for analysis that you need to be familiar with. Okay, got that so far? With those ideas in mind, we're ready to continue on. Oh, here is how we can calculate that. Obviously, you can see it's just T over T upper over 2 plus the core thickness plus T lower over 2. That's that H parameter. We're going to see that again on the next slide as well. The other parameter we can compute is just the sum of all the thicknesses that we see here is upper, lower, and core, since we only have 3 materials, an upper and lower face sheet and a core, which is probably one of the most common sandwich constructions. Okay, so let's take a look at our stress model. Here's our little typical sandwich, and we're going to have a few assumptions that we're going to apply, like the face sheets carry all the in-plane loads, and the core resist all transverse shear and point loads, and the core provides that shear continuity for resisting bending. Now, these sound like just more words probably, but if you think back from the beginning of our studies in structures, back to our first structures class or our structural mechanics class, which I labeled stress analysis 1 in my videos, you have seen right after we learned about axial loads, we learned about running loads. And then shortly after that, about the time we were getting into bending, we learned about lumping our properties, where we can just take all the area and put it in one area, all the area in another area, with everything in between, thinking of that as just a thin shear web. We use that all through. The idea is that those lumped areas are the only thing that provide resistance to normal loads, loads that are perpendicular to the cross section. And that thin web is the only thing that resists shear loads. This greatly simplifies analysis and it's often fairly applicable when we have lightweight structures or sandwich materials. And that's all these ideas here are saying. It's saying the face sheets are going to act like those two lumped areas. So we're just going to be carrying axial load in those, although we often can carry in-plane shear as well, and sometimes we'll need to do that, but not carrying the transverse shear, which we're going to force to go into the core, which is a pretty good approximation. The second one, that idea that the core resists all transverse shear and the transverse point loads, the transverse shear is that idea, just like the web of an I-beam, any transverse shear acting on the section, we're just going to imagine is just a average stress acting on the core, and that's it's close enough for government work. It's fairly accurate for these structures because of the different stiffnesses that we encounter. And then reminding ourselves that it's the core that provides shear continuity. So it's critical that the core is attached to the face sheet continuously enough, and it has enough shear rigidity and strength so that it forces the upper face sheet and the lower face sheet to act as one. So the upper face sheet can carry in-plane loads, the lower face sheet can carry in-plane loads, the core can take those transverse loads, and it transfers that shear from top to bottom so that they act as a single bending member. Okay? Critical idea. If you don't quite get that idea, it's actually not critical to do decent analysis, because all you can do is, if you learn to apply these formulas, it will drop out in your lap. However, this is completely knowable by anybody that's made it this far. So if you toy with these ideas, go back to those ideas, those lumped properties, maybe rewatch some of those videos in our stress analysis 1 and 2 playlists, then that can help you to nail that and master that idea. So let's look at our bending stress model. Once again, let's just focus on a cantilever beam. With this can apply to any kind of structure. So here we have a beam. We were fixed on the left end. It's got length L. We have an upper, lower, and a core thickness, and we have a point load on the end. Okay, now we already talked about this H parameter, which is the distance from the center of face sheet to center of face sheet, since we're assuming that upper face sheet carries all axial load and the lower face sheet carries all axial load. Those two carry only in plane loads. They're the only ones taking normal stresses, normal forces. The core is the only one taking shear forces. So that parameter from center line to center line, if the upper face sheet is carrying load, it's going to carry it right at the center. It's going to be acting like it carries it right at the center of that face sheet, which is going to be the midplane basically. Same thing with the lower. So center line to center line is the critical dimension. We're calling it H, and that's what we're going to use. Okay? Next, we've got, if we look at that, we can calculate our reactions. Now remember, you look at this and you think, well, we've got a force here, P. We're going to have a reacting shear, S, which has got the same magnitude. And we're also going to have a bending moment, PL. But remember, we no longer are dealing with a solid structural member. We're dealing with two rod-like members and one shear member. And that means all the shear has to move through the core from where it's applied at the load to the reaction. And that face sheet, when you apply that load, it just doesn't magically jump into that face sheet. What happens is that force is going to go down into the core. It's going to start being carried in shear. And as you move away from that force, that shear, which is acting down, is also acting this way on the face sheet, which is driving more and more axial load into the face sheet. So, and we're going to see this a little more clearly on the next slide. So what happens is, now if we know that the moment at the right end is just P times 0, so there's no load in the upper and lower caps. But when you move 1 inch, you're going to have that shear flow. P over H is the shear flow, which is going to start driving in that flow times that 1 inch is going to drive that much axial load enters that face sheet. And by the time we get to the left end, we're going to have all of it. So once again, we've got a free body diagram. We applied a point load at the right end. On the other end, we have a shear reaction. And instead of looking at the moment reaction, which is true, we have a moment reaction, but the way it comes out is a couple between upper and lower caps, because those are the only things that have normal stiffness. So actually the moment is just shown as a couple from upper to lower cap. This is a key idea. It goes all the way back to our stress analysis 1 playlist, where we learned about lumped sections. So with this in mind, we can see our upper and lower cap. If we just sum our moments about the lower left midplane of the lower face sheet, then we can see we're going to have P times L minus PU times H equals 0. That means PU is M over H. If we now sum our moments about the midplane of the upper face sheet, we're going to find PL minus the lower PL. What I'm saying is P times L minus PL times H equals 0. And we find out that the lower face sheet has also got a magnitude of M over H. Now, one of them is going to be tension. One of them is going to be compression. In this particular case, it's the lower cap that's in compression, the lower face sheet. But this M over L idea, which goes all the way back to statics, where we learned about couples, PH equals M, or P perpendicular distance. And in this case, the perpendicular distance is H. That idea is right here, bringing us to stresses that we can evaluate. So that's the force in the upper and lower cap. Now, a lot of times, since we have not just a rod structure, when we dealt with these lumped assumptions before, we just had rod-like structures, but now we're talking a plate-like structure. So often, instead of dealing with that as a force, we'll deal with it as a running load. So that magnitude of the force, M over H, divided by the width of the face sheet, that will tell us what the running load is. So that's another common way of seeing what this is. We can actually write that force as a running load. And then the stress is just that running load over T. And I guess we'll get to that in just a minute. What we're looking at here is the shear stress in the core. Once again, that force P, the only thing taking that, we're assuming those face sheets are too flimsy to carry the shear by themselves, but the core can, and we're going to assume instead of taking the whole distance, capital H, or just the core distance, TC, we're going to use that H dimension from midplane to midplane is what we're going to pretend carries that shear, and we're going to use the average value so that S over H is the shear flow, S over HB is the shear stress in the core. And then once again, our face sheet stresses are just the N over T or P over TB are two different ways of calculating the exact same thing, which means we could also write as M over TBH. So it's a little dangerous to go writing the stress just as M over TBH. It's better to think of it as we have what's the force in the cap, and it's just M over H. And then that force divided by the area of the cap, which is just BT. And also for the core, it's just P over H is the shear flow, and that shear flow over the thickness is the stress, is a very common way of doing that. In this case, for the core, the thickness we're using is not T core, which we could use. It's a little bit conservative. We can use that H as the representative value from midplane to midplane. So S over HB is the shear stress in the core. These are the basic ideas. Now, if you think back, we have covered methods with classical lamination theory that actually can analyze this composite sandwich. We would just have a 3-layer sandwich, a 3-layer laminate. We would have a face sheet at the 1 position, a core at the 2 position, and a face sheet at the 3 position. And then we can implement our method using exactly what we learned about in the last number of lectures, 12 lectures or something. But you'll notice here, by applying that lumped assumption that we've been using from stress analysis 1, we can do this even more simply with just statics kind of calculations. Everything becomes quite simple, and the values are reasonably accurate and match test data. And so this is a much more efficient way to analyze structures that's done nearly worldwide. All right. If we look at this idea further, so we already kind of broke down the stresses, but we also need to be able to, it helps to look at this in more detail. And the exploded free body diagram is a very convenient way to do this. Now, normally when we draw a free body diagram, I usually stress with my students, it's critical to also put all dimensions that you're going to need for analysis, or else I'll typically mark off points for not being a complete free body diagram. But for the purposes of our little methods here, we can look at this. We got 3 free body diagrams without, or 2 free body diagrams without dimensions. We've got the beam with its applied loading. We then have a free body diagram without dimensions. The only thing we're missing there that we need would be the L dimension. And then the key here is we're showing an exploded free body diagram where we take each of the piece of the members and we rip them apart and show the forces between. Now we've got this force on the right end. It's pulling on the facesheet. The facesheet, by definition, the assumption that we made, has no transverse stiffness. So that facesheet, instead of going into that force, instead of going into the facesheet, has to be carried by the core. So the core resists that. The core pulls back and it develops shear flow. P over H is the shear flow in the web. And if that's acting upwards, remember, shear stresses are romantic little mothers. So if this one's going this way, then on the upper face, it's going to be mouth to mouth. Those 2 little arrowheads are mouth to mouth. And then if you look at the other end of it, the bottom end, the little toes of it, that's toe to toe with the other vector. Those cute little vectors are a little mouth to mouth here and toe to toe down here. So once we get one shear flow drawn, we can immediately draw all shear flows on the section. So imagine we've got this block of core. We saw this point force. We know that point force can't be carried by the facesheet. It's got to be carried by the core. So we just take P over H. That gives us Q. That shear flow is acting like this, which means that romantic little shear flow is going to be met mouth to mouth on top of the core. And down below, that means it's going to be toe to toe. And on the far end, it's going to be mouth to mouth and toe to toe as well. So that gives us these 2 vectors coming together and these 2 vectors coming together with a core block between. Now, action and reaction pairs means if we focus on that upper surface of the core, we have these little shear flows going this way. That means they're the ones that are acting on the core like this. That means they're acting in the opposite direction on the facesheet. So you see the facesheet has a 0 load on the right end because there's no load applied axial there. It starts picking up. Here's the facesheet. And we have these little shear flows going, pushing it. So in 1 inch, it gets Q times 1, gets how much force is now on the facesheet. And 2nd inch, Q times the 2nd inch gives another piece. So we see that because of this action of the shear flow acting on the bottom of the facesheet, and the facesheet's like this, right? It's doing this. It's adding more and more force into the upper cap. So the cap goes from 0 to more until it has that PU value, M over H. In fact, if we took a cross section anywhere, we could take the moment, which is P times whatever distance we traveled, divided by the H, and that would tell us what the upper and lower cap forces are. But you can see the way that load gets in is as a shear flow from underneath. Correspondingly on the bottom end, you'll notice that block of material had the shear flows going this way. So they're going in the other direction acting on the facesheet. So that lower facesheet have these little shear flows pushing more and more load into that facesheet. And then that's reacted out with the force. So this exploded free body diagram is quite helpful for understanding what's happening. If we just sketch out what our loads are on this, remember the shear flow is just S over H, which S in this case, the total shear is just P. And the upper and lower caps are both just M over H. One of them is compression and one of them is tension. We have exploded free body diagram. The analysis now of this structure is so simple because all we need to do is evaluate that core, that Q, turn that into a shear stress by dividing by the width, by dividing by the thickness. That core, all we need to do now is divide that shear flow by the width of the beam. That's the other missing dimension. And now we know what the shear stress in the core is, and we can compare that to the core allowable. And the facesheet, we can look at the max load in the facesheet, turn that into a stress by just taking that P divided by BT, and then compare that to the tension and compression allowable of the facesheet. We'll learn about tension and compression allowables of the facesheets and the sandwich structures in the next lecture. Got those ideas? Okay. Now that we understand, now you'll realize, oh my gosh, sandwich structures, I thought that was complicated. That was so simple because we use that lumped assumption. And that's the key. Now we're going to do the same thing when we evaluate deflections. The deflection model is a little more challenging, but actually it's completely doable, and we're going to make it simple for you, so stick with me. So now let's figure out, okay, how do we evaluate the deflection of beams? Okay, well, so let's go back to our cantilever beam with the same nomenclature we've been using, and we can see because of this load, we're going to get a bending deflection due to its normal stiffness. Now, this is what we've been doing from 3261 when we started calculating deflection of beams. We use the axial stiffness of the beam, the axial stiffness properties, which is what happens when we relate the 1 over EI times the M dx. When we integrate that puppy to get the deflection, that's all that is, or excuse me, differentiate. We integrate to get the deflection and then integrate back to get the differentiate to get back up to the other. So since we've been doing that, we've been seeing that the deflection of the beam, that deflection of the beam is just based on axial properties of the beam. So next, let's take a look at how the beam responds in deflections to the loads applied. Now, if you think back from the beginning of of our structure stress. Okay, so next let's take a look at our deflection of the beam. Now, if you think back, we've been dealing with deflection of beams since our Stress Analysis 1 class, Structural Mechanics 1, when we started dealing, right after we covered bending stresses, we learned about deflection of beams. Now, when we did that, what we focused on was the axial stiffness properties of the beam. Remember, we related the moment. We took the loading on the beam, we integrated twice to get the shear and then the moment, and then we divided that moment by EI and integrated, and that gave us the slope, and then we integrated again to get our deflection. All of that was only using the E and the I, not the shear properties of the beam. So what we were actually getting was the bending deflection of the beam accounting for only bending stiffness or axial stiffness. It's the axial stiffness that was resisting bending. And this is the dominant thing that resists bending when your beam is long and relatively thin. But the thicker and stubbier your beam gets, and that's partly a function of the relative stiffness of the materials, the more our shear deflection comes into play. Now, shear deflections were back in one of our first lectures of our Stress Analysis 1 class as well, when we looked at a little plate that was really stubby and we looked at a force and how that thing just kind of went, not the continuous deflection, but more like a discrete, the whole thing moving down as a unit kind of deflection. So in order to evaluate sandwich structures, we're typically going to want to evaluate both bending and shear deflections. Bending deflections are familiar to us and are becoming intuitive. However, we're going to have to tweak what we were doing or else we can't apply them to sandwich beams. So I'm going to show you how to do that. Then we're going to learn, now those shear deflections were a lot less intuitive. Whenever we run into that, we tend to kind of lock up. But I'm going to show you a simple way to account for that as well. So we've got the bending deflection, that's what we're talking about here. We've also got our shear deflection, which we're going to look at. Remember, that was shear deflection is just gamma L. When you just look at that whole thing ratcheting as a unit, you'll notice the first one with it, where the axial properties were used to evaluate the resistance to bending. We get a nice continuous change as we get more and more deflection. But because it's how those little strips of the beam stretch or compress, and that stretching and compressing is what causes or resists that bending. With the other case, we were looking at how the shear properties of the beam resist that motion, which gives us a rigid dropping kind of deflection. So both of those, the first one we're familiar with, the second one we've done also, but it's a little less intuitive. We kind of left it behind when we're talking about deflections. So because, once again, because our cores tend to have really low shear stiffness, tend to be rather thick, and our beams tend to be stubbier, we're going to want to be able to account for that. This is our bending deflection, and this is our shear deflection. And if we add those together, we're going to get the total deflection on the beam, and that's how we're going to get this. It includes both shear and bending deflections. So we're going to lay out a method to do this. To do this, we're going to need to be familiar with a couple parameters. This is a core stiffness parameter, which has that H and the thickness of the core and the modulus of the core, and an axial bending stiffness parameter, which is the Facesheet modulus and thickness and the H dimension and Poisson's ratio. Now, if you look at that second term, that D, since many of you are probably going, the alert reader is going, oh my gosh, we just dealt with that when we were talking about classical lamination theory and looking at our whole bending matrix. We saw that first term was a D term. In fact, all of them are D terms, but that's the one that corresponds with this kind of deflection. So yes, this is the same kind of term. There we were doing a classical lamination theory of the laminate, which could be done here, but it's much simpler to just calculate the D of this 3-ply lumped assumption sandwich beam. And if our face sheets have equal thickness and they're the same material, then this equation can be used. If the two face sheets are different material and or different thicknesses, we need a little more ugly equation, but no big deal. This is what we're going to need here, okay? So hold these thoughts. These are some general ideas that we're now going to take to ground on the next slide. All right, so bending deflection. Let's think about that first. Remember, what we're going to do first is calculate our bending parameter. Either if we have the face sheets of the same thickness and material, we use the first equation. If they're not, we use the second equation. No problem. If you want it to be simple, you can use the second equation for everything. And sometimes you're just doing a little more work, but then you don't have to think. Next, remember, we saw in the last couple lectures, we saw that our dB parameter, that bending stiffness D times the width of the beam, is equal to, it's analogous to the EI, the modulus times the moment of inertia. So remember that. And then what we're going to do is we're going to go to our handbook. In the appendix, we have a bunch of canned formulas for different kind of constraints and loadings. Find the most representative one. And then what we'll do is we'll use that by plugging in wherever it says EI, we're going to plug in dB instead, and that will allow us to calculate the bending portion of the deflection. Once we have that, we're ready to deal with our shear deflection. In order to do that, what we're going to do is first get these two parameters, Kp and Ks, from this table here. Okay? I'm calling them Kp and Ks. One of them is a factor that has to do with the loading, the way the load distributes across the beam. The other one has to do with the way the constraints are located, okay? So all we got to do is say, well, if we have a cantilever beam, we can see our Kp is P and our Ks is 1. If we have a distributed load on a cantilever beam, our Kp is WL and our Ks is 1/2, and so on. You just look up your beam. If you can find it here, you can grab the two parameters and plug it into the equation I'm about to give you. Now, if you can't find your beam constraint and loading here, then you have to actually calculate your own Kp and and Ks. That's a little harder, but basically what this is done, the way this is done, it's going back to the idea that we saw in our third lecture of Stress Analysis 1. We saw that deflection, the shear deflection, was just the shear stress divided by GL. So if we had a constant beam, that's pretty simple, as some of these are. Constant beam without a change of stress across the beam. We can see this, but if our without a change of shear stress. Remember, the first one is changing axial stress from end to end, but the shear stress is constant. That's what makes that so simple. If we have a change of shear stress along the beam, or a change of material properties along the beam, then we actually need to integrate up the effects of those, and that's how these coefficients are calculated. otherwise. But if we can find our beam here, we can just grab those numbers and plug them in to this equation right here. Plug in our KPKS, the length of the beam, the H parameter, the core shear stiffness, and the width of the beam, and that gives us the shear deflection of the beam. We now can calculate the total deflection by adding those two puppies together. Simple. So this method will allow us to get fairly representative deflections of beams without too much complexity. It's very cool. Now, we could have, once again, used classical lamination theory to get properties, but then we would have had to do something tricky here to get our deflections, something similar to what we just did. But the sandwich idealization, where we're using those lump parameters, really makes this simple to do. So that is how we're going to evaluate the stresses in sandwich structures. Next lecture, we'll talk about the strength of sandwich structures. We're going to take a little more look into a few design parameters, just scratching the surface. For example, core materials can be, honeycomb is very common. There are different kinds of corrugated cores. You can build truss-like structures in there, and you can use foam materials. But one common material is these honeycomb materials, which are generally, it's formed by thin sheets. Often it can be aluminum, it can also be Nomex, or just about a number of other materials. If we have like let's say an aluminum core, imagine your aluminum foil that you wrap your food in. You know how soft and pliable that is. But imagine taking a sheet, forming it into a corrugated piece, and then bonding those cells together and then expanding it into these little hex-like cells, one after the other. That's kind of how a lot of this is formed. And there are actually some folks have like proprietary methods for actually welding some of these things together for higher strength applications, or excuse me, higher temperature applications. There's a number of different proprietary methods for that. But basically, the basic idea is we have a core. When we're all done and we've expanded that, what we end up with, even though each little foil is extremely thin, when it acts together as a whole and is bound in between the face sheet so it can't move too much relatively, it has pretty good shear stiffness in both directions, although the two directions will often be different properties, both in terms of modulus and strength. And we also can get pretty good crush properties of that, and sometimes very ideal crush properties for certain kinds of applications. So that's just a baby glimpse into this. Hexcel, a couple of references are here, has a lot of materials on that help you to get familiar with their products, and there are other folks that make this kind of stuff as well. Here's just a little glimpse at some of the properties. You'll find a few more materials in the appendix of the handbook, Appendix C, where we're going to look at, have some properties that we can play with. Here are some common aluminum honeycomb materials. This is given by cell size and by material and by foil thickness. Sometimes it's called out by density, sometimes by foil thickness. You can see we've got compressive strength, the bear strength, and the stabilized strength. That has to do with the transverse crushing of the material. That bear is like that first little peak. We'll talk about this a little more next lecture. And then we can see for shear, which is the primary usage of the core, because remember, we're assuming it only takes shear stresses in our bending designs, and for sandwich kind of beams, then we're going to have a longitudinal direction, that's the ribbon direction of that foil, and a transverse direction, that's the W direction. You can see we have a typical and a minimum value. Typically, we'll use minimum values. We will typically use minimum values for analysis, although there are some applications where you can justify using a typical value. We use a typical modulus and a minimum strength. So you'll notice we have a modulus for both longitudinal direction, the foil direction, and the transverse direction, and a strength. A couple years ago, I was working on a project where we were working on a rigid barrier, and we were using it for another application. We looked at the strength of the barrier turned out the thing had been designed so the strong direction, the longitudinal direction, was sideways, which means it actually wasn't good for the prescribed loads that it was designed for. It's a big problem. Small oversight, big ramifications. It's critical that we understand our product, what direction it's used, what its strengths and weaknesses are, and make sure we engineer it in such a way that it's built exactly like we planned. So here we have the right side of this table, plate shear. We've got the longitudinal direction and the widthwise direction. We've got the strength and the modulus. We're typically going to use the typical moduli, and we're often going to use the minimum strengths, although you could justify using typical strengths for certain kinds of applications. All the stuff to the left for compressive and crush, that's talking about when we're doing analysis for those punch loads and how they crush the core. And HoneyComb has very ideal properties for certain kinds of crushing things. This crush strength is that strength once you're going to get a little peak, and then it's going to kind of stabilize out. And that's a pretty good, pretty useful number for another application. I may have a separate video on that. Mainly we're going to be using these shear direction properties for core for most of the stuff we're going to do. And we'll use that crush every now and then to make sure that we're not punching into the core with point loads. Okay, so once again, there's a lot more that could be said on that. You can access HoneyComb's products and also be watching for more videos, because I'll be having more content coming out for guidance on that in the future. So just some ideas, if we just look at some different design ideas. So now this, if we do have a honeycomb kind of structure, and even we have a foam, what happens is a lot of times with composites, moisture can be an issue, and other contaminants. So imagine having a honeycomb core which has a bunch of open flanges, and you come to the end of the product and you've got a place where contamination and moisture and other things can come in. So a lot of times we'll come up with some fancy way of doing that. One is just filling that with adhesive. That's a very common method. Sometimes they will go and densify or crush the core as you near the end so it gets a lot more solid. That can also be done for some applications. This shows that they've folded the facings over and either bonded them or fastened them with a little fastener through there. That also can be done. Often what they'll do is they'll bring a lower density core, which is designed for the bending properties they need. And then when they get near the end, they'll drop in a little strip and bond it in of higher density material, which has higher strength near the edge. This has the effect of allowing fasteners and things not to crush that soft core. We do similar things with other composite structures. Another way is to bond in a little angle or a Z or a C channel, which could have higher density core in it, or could just all be bonded with adhesive, or even have void structures with bonding around the edges. All of these are different ways. This little taper design, you'll notice here what they've done is they've realized that when you attach through it, you've got bearing problems if you've got a really thin face sheet. And some of these designs give you more thickness for dealing with that. But one way is to just taper your face sheet so they get thicker, and then support them with a higher density core. And all this would be bonded top, bottom, and between the different members. This is another one where they fold over the face sheet and then they thicken up or maybe slip another piece of reinforcement material in there. This is a little higher form where they lay that face sheet over and slope it down and then fasten it together. Once again, now when you pull on this thing, you can see it's going to tend to pull it apart and pull a little tension stress right where that's bonded together at the neck of that little leg. So while this is commonly done, you got to be careful with your design. Make sure you've tested enough or analyzed enough to understand all the stresses. Another design that's a little better, gives a little better resilience potentially against that kind of tension would be if you just make that edge solid. This is kind of what we did with on the Delta program, where we would bring our composite sandwich. We had graphite epoxy face sheets. We had a Roacell foam core. We went with a higher density core as we got near the edge. And then we would often go with a solid laminate in the end where we were fastening through so you don't have crush issues and you got a nice solid reaction. That ended up causing quite a bit of extra analysis when we had, very cold liquids and things on one side of the face sheet and very hot and humid environments beating on the other side, and looking at the thermal and strength distribution, load distribution through the thing when you have this gradient of properties and moisture and everything else. Here's another way. This one also folds down that, but the way it does is by crushing the core. You got to be careful because you don't want to. So failing in such a way that it's continuous and just changes properties is one thing. Failing in such a way that it actually loses continuity is another thing. So depending on what your core material is, you have to be very careful because you can limit yourself on some of the options. The next slide, I have a few more, and some of these are the same. These are the other. I referenced the other document that those were from. I think it was from Handbook 23. Here, these are from one of the Hexcel products. Is showing some of the ways that they recommend, and a lot of these are similar to what we saw in the last one. This just shows briefly how to densify your core, or kind of what that means when you take that foil and you're crushing it together. What this is showing is now when we have point loads, so the main thing resisting point loads is going to be that core property, which means we might need to drop a core plug in, which I'll show you in a minute. Another thing is when we have loads applied, we may need to thicken it up so we can put an internal or an external butt plate. Now the internal butt plate needs to be put in there during the initial design before you lay the upper face sheet on. Otherwise you have to cut away face sheet and drop that in and bond it all in there and then put your face sheet back on. So different ones have different benefits. Whenever we have like a point load, like let's say we have a fastener with maybe an antenna or something that's putting bending into the localized bending into the core. Now the core is good for bending, but you got to get that load into the face sheets. And so a lot of times we'll put a higher density plug in there. So you'll cut like a hole through the core, and you'll drop in a higher density material, and then you'll bond your face sheet on top of that. That can either be done initially or be added with doublers and things. This higher density core could be a higher density honeycomb. It could be a solid graphite epoxy puck. It could be a solid material. You name it. Folks have probably done it. Sometimes they'll stick like a little metal extrusion, like a little channel, box section can give you a nice little hard point for applying loads. And you can see that thing, if you have point loads, it's going to drop shear into the core and also can drop the torsion into the face sheets fairly well. This is kind of related to one that we saw before. Here's another foam core where it's going a higher density foam core insert, kind of similar to that first one. If we have inserts, a lot of times we're going to drop fasteners through the material. I usually, whenever I do this, if it's not a part that needs to be removed, I like to butter up the fastener. So the fastener is completely coated with adhesive, like EA9394 or something similar. Underneath the head, I'll often use a washer when I can to get bonding against the face sheet, and underneath the washer below and underneath the nut. So it's all bonded together. And the thing you have to be careful of when you're putting fasteners through core, a lot of times the core, once again, has a lot lower crush strength. So just a little bit of torque on that fastener can crush that core. So you need to analyze how much turn on the nut can I get without crushing the core, failing the core. And you can go back to the video when we talk about tension-loaded fasteners in our Stress Analysis 2 video. We talk a little bit about turn on the nut and how you can estimate the preload from that. And you can use those properties for evaluating the sandwich. Right now I don't have that. I may be adding more content to our sandwich structure lectures to show you how that's done. So stay tuned. Make sure you subscribe and stay tuned for that. So these are some different ideas. We've got some where we have the fastener going all the way through. That has the nice idea of being able to drop a moment as a couple between the face sheets. Sometimes we'll put an insert that doesn't go all the way through, and then you got to be careful to make sure that the core has rigidity, because if you have a loading that has any torque, it's going to tend to try and wiggle its way out and fail the core and the adhesive around there. If you go face sheet to face sheet like this lower right design, you'll see now you're dumping load into the face sheets and into the core. That's a better design, not always practical for putting it together. So these are some different ideas. And then here's some more ideas from another of those references where we have like formed extrusions and other kinds of hybrid and single part kind of joints. All these things can be done. So So that kind of gets us started on sandwich structural analysis. The first thing is to understand what those are and what key parameters we need to define to analyze those. Then, going back to our lumped property idealization with just areas and a shear stiffness is a very practical way. You'll notice the equations were quite simple. Some of the easiest we've used. Make sure you spend enough time in them to master them. Then for deflection, we have our normal deflections, our bending deflections, which we can use by just using the dB equals EI parameter in our current bending equations. And then we have the shear stiffness, which we haven't dealt with as much, but I gave you a nice easy way to evaluate that for a number of beams. We just sum those together. And then we have some basic ideas on the closeouts and different things we can do there and with design parameters. Stay tuned for more content. Now, next lecture, we're going to look at the strength of these beams, and that's a critical idea. And then we may have some follow-on lectures on some of the other nuances of evaluating and designing beams. So stay tuned. Enjoy.